5 lectures on this. Markus Luty. Markus it's an expert in the field of particle physics, quantum field theory, and it's a reference in the field worldwide. And comes to us, initially he did his PhD at the University of Chicago some time ago, let's say. And then after a position at Berkeley and somewhere else, MIT, yeah, one of those places.
One of those places.
MIT. He was a professor at the University of Maryland, after which he moved to the UC Davis, where he is now coming to us. So, Markus, whenever you're ready, give us your expertise.
All right. Thank you very much. It's really a tremendous pleasure for me to be here. Just a couple remarks. First of all, when I was a student, I never did go to any summer school, okay? And so I certainly, now I've lectured at a few of them, and I've sent my students to them, and I know what they're like, and so I think you should be grateful to be here. I think it's a real privilege, and I hope you're making the most of it. This is sort of my unofficial motto when I teach. So I tend to teach pretty slowly, okay? And I really want you to interrupt me. I really mean that, because if nobody interrupts me, I assume that I've either lost you or I'm boring you, and sometimes it's hard to know which, okay? So I really mean that. I really would appreciate it if you'll interrupt me all the time with annoying questions, okay, which will not annoy me. So this is the list of topics that I'm going to talk about, and I can understand if some of you might look at these topics and be a bit disappointed because there's nothing cool, shiny, new here, in a sense, okay? My goal is to try and talk about what I think are the conceptual issues with the standard model, and I'm going to borrow a meme from this morning's lecture. I think this perfectly summarizes how I feel about the standard model, how I think you should feel about the standard model. I've spent a lot of my career trying to kill the standard model, trying to find things wrong with it, trying to find things beyond it, and yet at the same time, we love the standard model, right? We have to really understand it. If we're going to kill it, we have to love it, we have to understand it, and that's what these lectures are about. My generation has failed, okay, to do this. So this is me trying to hand this over to you, okay, because the next generation, I hope that I can excite you guys to think about some of these problems, and that's the goal of these lectures. Just one thing, just so you don't panic, if you notice there are 5 topics here, and guess what, there are 5 lectures. I am more or less going to be following this order, but when we get down here, it's going to be moving around a little bit. So don't panic if we don't, don't worry if we're not here at the end of lecture 2 or something like that, okay? I don't know what's going to happen, frankly, but I don't want you to panic, okay? All right, I don't know if that was reassuring or not. Okay, let's start, okay? So I want to start with some very basic and general statements, okay? First of all, every physical theory that we have is approximate. Everyone, including the standard model, okay? And if we think, and every theory we've ever had, of course, has been approximate, right? So why have we been able to make progress? We've been able to make progress because we don't need to know everything to understand something, okay? And if we look back, it's amazing with what our ancestors, our predecessors were able to do with how little they knew experimentally, right? And so all of physics is based on approximations, and in fact, it's almost always the same kind of an approximation, okay? Namely, it's an expansion that involves a scale hierarchy, okay? And so let's just talk about some very, very simple examples, okay? So let's look at the multipole expansion in electrodynamics, okay? So what is this? We have some region that has some charge. This region may have some size A, and I'm interested in finding the electrostatic potential at some point, let's say a vector r, okay, away, okay, and I want to find the electrostatic potential at that point, okay? So we all know the answer to this. There's a multipole expansion of this. So the lowest term is just the total charge of this in this region divided by r, okay? And that is the leading approximation at long distances. But then there are higher order corrections. I can write this as q1 ri over r to the fifth, r cubed, sorry, okay? This is the dipole correction, right? And then I have a quadrupole correction, has two indices on it, ri, rj over r to the fifth, and so on, okay? Now, why this is usually a fantastic approximation at large distances. Why? Because these multipole moments that I'm calling Qn, what I generally expect, if I just look at some random charge distributions here, I expect that they should be something like Q naught times a to the n, okay? In other words, if I have a sort of an arbitrary charge distribution here, which has a characteristic size a, then this is what I expect, right? And then this first term here, for example, is of order Q naught over r times a over r, okay? So it's suppressed by a factor of a over r compared to the leading term, and similarly this term is Q naught over r, a over r squared, and so on ad infinitum, okay? So what do we learn? This is a very simple example, but it's very paradigmatic, because what we see is that if r is much, much greater than a, okay, we only need a few multiples to get a very accurate answer, right? We don't need to know the complete charge distribution. On the other hand, if we probe to shorter and shorter distances, and we probe down to the distance a, the whole expansion just breaks down. Every term is the same size as the term before it, generically, and this expansion doesn't converge. Okay, so we lose convergence. Okay, and the way we interpret that is that there's some kind of more fundamental description that we need to use that has fewer parameters in it, right? So we call that, in particle physics lingo, we would call that new physics, some new model, some more microscopic, detailed understanding of what's in here. For example, historically, this might have been an atom, right? An ion, something like, or a molecule, something like that. Okay? So this really simple example, actually, even though it's incredibly simple, it's static, you know, this illustrates the main ideas that I want to talk about, because here, in this regime, where we have a big hierarchy, we're able to have a predictive theory without knowing the details of the underlying dynamics. So this is, we could call this lots of different things, but I could call it universality, right? This behavior here is a universal behavior that's given to us by, you know, electrodynamics at large distances, right? Okay. On the other hand, here, this interpretation that once this expansion breaks down, we're actually finding some kind of, that we're uncovering some kind of new physics that we have to understand in detail. This is how the progress of physics has been going for its entire history, and this is basically reductionism, right? Reductionism is the idea that that there exist simple underlying explanations, right? Okay, and we don't know that that's true, but it's worked pretty well so far. Okay, so that's my 5 lectures in one nutshell. Let me just do one more example. Okay, so another example I could give would be fluid dynamics. Okay, classical fluid dynamics. This is much more similar to the kinds of things that we're going to be doing in particle physics. So as you know, the underlying picture is that we have some molecules that are bouncing around. That's the microscopic description. And there's some characteristic scales associated with this. There's the mean free path, which is a length, mean free path, right? Mean free, it's not called the mean free path. What the hell is it called? The mean free path. It doesn't make any sense. It just occurred to me, it's not a path, it's a length. Anyway, okay, you know what I mean. Stop me if you don't know what I'm talking about. Then there's also the collision time, or equivalently, it could be the characteristic velocity, right? It's lambda over the characteristic velocity, right? And of course, these are only sort of defined at the order of magnitude level, but the idea is that if our spatial resolution, this is our resolution, right, is much larger than the mean free path of a molecule, and our time resolution is much larger than a collision time, okay, then we only see the sort of average redistribution of mass from these molecules, and we can describe this using classical fluid dynamics, okay? And I had to look this up. Here are what are the fluid equations of motion? Okay, it doesn't really matter. This will not be on the exam, okay? Okay, but there's a pressure term, and this is this famous Euler term. And these terms right here are completely model independent, okay, right? They do not care, I mean, this P does, basically these terms don't, I'm simplifying just a bit, but these terms don't care about the structure of the molecules. But then we have viscosity terms, okay, and these do start caring about the behavior of the molecules, okay? So if you stop at the viscosity terms, it's kind of like going to one higher order here in this expansion, okay? But if we start probing things at this microscopic scale, we can't use fluid dynamics anymore. We have to completely change the description and start talking about molecular dynamics, okay? And so what I'm going to try to convince you of in the course of these lectures is that the standard model is not just analogous to these examples. It is exactly like these examples, okay? So I'm trying to bring quantum field theory back to Earth, okay? Because sometimes if you look at a quantum field theory book, it's full of, I don't know, dimensional regularization, all kinds of complicated technical things, and it's hard to learn it, right? And it's easy to lose track of the fact that this is physics. This is physics. It fits into the same paradigms as everything else in physics. And so that's what I'm going to convince you of, okay? Okay, you may, all right. Okay, so let's finally talk about quantum field theory, finally. Oh, only less than 15 minutes in, that's not so bad, okay? So what we call quantum field theory is, of course, relativistic quantum field theory, and that means that we are typically interested in highly energetic processes where the typical velocities are of order the speed of light. We're also interested in quantum. What does quantum mean? No, it does not mean things are small. It means that if we look at a typical process and we compute the classical action for that process, it's not much bigger than h bar, okay? So that is what makes something quantum mechanical. So intuitively, it means we're talking about a few quanta, few elementary particles, processes like that, okay? And it's for these kinds of processes that it is useful to use units where h bar and c is 1, okay? It is useful. Okay, so usually this is simply something that's foisted on you with no explanation, one of the many things that's put between you and understanding what's going on in these quantum field theory textbooks, but I'm going to try to explain to you why this is so useful, okay? All right, so just some other notation. In these units, okay, everything is units of mass, as I hope you know, so if I have some physical quantity x, I can always express it as a mass raised to some power, and I'm going to be using the notation that the mass dimension of x is that exponent, right? So masses have mass dimension 1, obviously, and lengths have mass dimension -1, for example, okay? Okay, so now let's illustrate. This is something you've seen before. I hope you wake up now, because now I might be telling you something you don't know, although maybe not. Okay, I'm going to talk about just a theory of a single real scalar. Okay? okay? And the other thing that you're always told when you study this theory is that we define the mass dimension of the scalar to be 1, okay? But now I want to ask why. Why do we do this? Does anybody know why we do this? Yeah, but why? Yeah, we're going to set the kinetic term to 1 or 1/2, but why do we do that? Why? Who cares about the action? I mean, let me tell you why, okay? There's a good reason why. Let's just do this and see what happens, okay? So I'm going to organize all the terms by their mass dimension, and I'm going to write them all in terms of a scale m. Okay, so that's just a way of keeping track of the mass dimension. This is dimensionless, and all the mass dimensions are absorbed into m. So I have a single operator. This operator has dimension 2, okay? And then I can write an operator of dimension 3. What do I want to write? I guess I want to write 3 factorial, whatever. Okay, and then I have m phi cubed that has dimension 3. Then I can write my kinetic term, which for reasons still not completely clear, I'm going to write as dimension 4. And then I can also write a dimensionless phi 4 term, but then I can just keep going. All right, and I can put a c phi to the 5th. Now this was 1 over m phi to the 5th, and I can write terms with derivatives, okay, like c phi d phi squared over m times phi d phi squared. So this is dimension 4, this is dimension 5, and obviously I can keep going forever. Okay? Now, what I claim is that because we have chosen these dimensions, okay, this Lagrangian right here is an expansion in powers, let me just write it like this, in e over m to some powers, okay? So when I write this, this means it's some integer powers of e over m, okay? So it's actually going to take me a while to explain this. I'm actually going to explain it. This is my claim. And like everything that you really want to understand, you have to understand it in at least 2 different ways. So I'm going to, first of all, explain this from the top down, okay? In other words, I'm going to assume a more fundamental description, just like I could assume a more fundamental description here, and I'm going to show you that this Lagrangian describes a long distance or low energy expansion. That's the top-down approach. Then we'll also understand it just from the bottom up. If I don't know what the fundamental physics is, I can still understand this as an expansion, just like in the multipole case. I don't actually have to know the details of this to understand why these terms are getting smaller at large distances. Okay, so that's the plan. Okay, so first I'm going to take the top-down picture, okay, because it's very concrete. Okay, there's no, I like to avoid philosophy as much as I can until the end. Then there'll be a lot of philosophy. Okay, so I'm going to consider a more fundamental description, okay? So my more fundamental description is going to have my scalar that's going to have mass little m, okay? And then I'm going to have another scalar that has mass capital M that's much larger than little m. So in other words, I'm assuming a hierarchy, okay, in the scales of this problem, okay? And now I'm just going to tell you, you don't get to argue with me, okay? You get to argue with me about everything, but this is the example that I chose. You can't get me to change my example. So I'm just going to use an example where I have a kinetic term for phi, and then I have kinetic term for my heavy scale eta, okay? And then I'm going to have some interaction terms. And to keep the discussion simple, I'm going to focus on a single interaction term, okay, which is a cubic interaction term between 1 eta and 2 phis. And so this is going to give me a Feynman rule. My phis are going to be dashed lines. My eta is going to be a solid line. So I have a Feynman rule like this, okay? And here G actually has mass units of 1. Okay? Now, in a realistic theory, there'd be there'd be quite a few other terms, okay? But I'm just going to focus on this one to make my point, okay? Okay, so that's it. That's my string theory. Now, the question is, what is the behavior? What if I take a look at this theory at energies, if I now restrict myself to energies far below the scale capital M, the scale of the eta mass, okay? Then I can't produce eta particles anymore, right? So if this is the highest energy collider in this world, I don't even know that the eta particles exist, probably, right? But I'm still able to do physics, just as we were able to do physics without knowing about the muon. The muon was discovered, it was a surprise. Nobody saw it coming. So in the same way, there should be some kind of a description that doesn't have the eta, that still describes the low energy regime of this model. So what is it? Well, we can understand what it is. We can start to understand what it is just by thinking about the process that you can do in this regime, which is phi-phi scattering, right? And so if we keep only the interactions that we have in this fundamental theory, the only way that phi interacts is through this coupling that involves the eta, okay? So we have effects like this, right? Plus cross diagrams. Okay, so just at tree level. And so what is this? We know this. This is a problem we know how to do. So we just have something like this. We have to put in all the cross channels. How come nobody's asking any questions? I'm getting nervous. All right. All right. Okay. All right. And so now the thing is that S, T, and U, okay, are, what do I mean by E? It's precisely things like this that I mean by E, right? And maybe also the mass squared. Okay, so these are all experimentally accessible energy scales that I'm calling E. So since E is much less than M, I can just expand this in these powers. The first term is just 3g squared over m squared. That's clear, right? I just set S, T, and U equal to 0. That's what I get. The next term I get is 4g squared m squared over m to the 4th. So what happened there? Does anybody know? Where did S, T, and U go? Okay, time to wake up. Remember, S plus T plus U is 4m squared. Okay, so it turns out that the linear term in the Mandelstam variables is proportional to the sum, and that you can see that. Once you see it, it's clear because we have crossing symmetry, right? But then the next term actually does involve S, T, and U in a non-trivial way, and it's S squared plus T squared plus U squared, and obviously I can keep going forever, okay? So what you see is that in the fundamental theory, I can do this sort of analog of the multipole expansion. I can just expand in powers of my IR scale divided by my UV scale. That's what I'm doing here, okay? So the fundamental theory clearly has an expansion in powers of E over M, okay? Now what I want to claim is that we can reproduce that expansion precisely with an effective field theory, in fact, with the one that I already wrote down over there. Okay? So that's what I wanted to show you, is that this generates an expansion in E over M. And in this case, you can see this, okay? You can see that this amplitude that I've calculated right here can be reproduced by the following effective Lagrangian. I have my kinetic term, nothing's changed there, and I have to put in a quartic interaction, okay? And I have to put in an interaction which I didn't actually write over there, C of d phi to the 4th over m to the 4th times d phi squared all squared, okay? So a lot of the terms that I wrote over there are 0, and one term that I didn't write over there is non-zero, okay? And what you can show is that what are these coefficients? If you want to reproduce this scattering amplitude, you have to choose this guy to be something. The details are not important here, but I'm giving them to try to tell you this is an actually true, precise statement. And this thing is much simpler. This is 2g squared over m to the 6th, okay? So now what's very easy to verify, you should be able to see right away, is that these things have the correct dimensions, okay? In other words, I guess the way I've written it, I'm sorry, this should be, let me write it like this, okay? So, yeah, okay, yes, okay? So these things have the right dimensions, okay? They have the right number of powers of g, and the powers of m are fixed by dimensional analysis. These kinds of corrections here, notice that these are small corrections. This is small compared to 1. So if I'm not interested in super high accuracy, I can just keep this term. I'll leave this as an exercise. If you haven't done this kind of an exercise before, you should think of this as a homework exercise. And please correct it. I think the coefficients have like a 35% chance of being wrong, maybe higher. Okay? So don't wake me up in the middle of the night if you got a different coefficient here, okay? All right, so this seems pretty straightforward. So another thing to point out here is that what is the reason that this worked, okay? So first of all, this idea of determining these coefficients by making sure it reproduces the fundamental theory, this is called matching, right? So I am matching an effective field theory to the fundamental theory. Okay, but why does it work? Okay, it works because I'm integrating out a heavy field like this, okay, then I'm generating some powers, some integer powers of the energy divided by the mass. And polynomials in the kinematic variables translate into local terms in the effective Lagrangian, right? So we know that if we write down any local interaction in a field theory, even if it has a lot of derivatives in it, as long as it has a finite numbers of derivatives, it'll just be a polynomial or a monomial in the momenta, okay? Okay, now this seems a little bit too simplistic, okay, because what about loops, okay? So you may think, well, my goodness, look at this.
Excuse me?
Yes, absolutely. Thank you. Thank you. Yes. Yes.
Okay, I thought you were going to explain it before, but at the end I think you just skip it. You were saying that we force the dimension of the real scalar to be 1 because otherwise we are not having this expansion in U over M, right? But
I never explained it.
yes. But
yes.
My point is, I could have, this is the way you wrote the Lagrangian. I could have taken, for example, a redefinition of phi and take the square root of phi. And in this case, the mass dimension will be 1 over 2, right? And we could say the square root of phi is our fundamental field.
Yes,
and
you're right. In some sense, it's just a convenience. You're absolutely right, because it is, after all, a choice of units, okay? But I agree with you that I haven't explained it yet, and maybe there will not be a big moment where I'm going to explain it. But the basic idea is that once we make this choice, the sort of identification of how important different terms are becomes essentially manifest, okay? So where I'm headed, for example, if we just assume that this G is numerically of some order 1 number times m, okay, then what you would find is that these terms right here really are a dimensionless number divided, an order 1 dimensionless number divided by powers of m as given by this dimensional analysis. So it's true though that there's nothing super duper fundamental about it. Okay, that's true. Okay, thanks for the question. Anything else? Yeah, you know, when I said interrupt me, I also meant, you know, I do tend to get rolling, as you know, and then I just, you know, I'm in my world, so it really helps me. So you will maybe really have to interrupt me. So I really appreciate the way you did that. Yeah, good.
Just for be sure, this expansion is like binomial expansion. I don't know if I get it on the Mandel-style variables.
Well, all I'm doing is a Taylor expansion in powers of s in this term. So
Okay.
the first term is just s equals 0, which is minus 1 over m squared.
Okay.
And that gives me this term. The next term
Right.
is linear in s, but I have a linear in s, linear in t, and linear in u.
Okay.
And because they add to 4m squared, I get something like this, and then I just keep going.
Okay, I got it.
Yeah,
Thank you.
it's exactly just a Taylor expansion. Okay, thanks for the question. Okay? Okay, so now I want to talk about the, at tree level, when I was a kid, there were people older than me, not necessarily wiser, but certainly older, that said that this kind of thing certainly breaks down at loop order, okay? At least one of these people has a Nobel Prize, but they're still wrong, okay? So let's what's the problem? What is the problem? Why are loops different? So let's focus on this term, which has a non-zero coefficient in the EFT. You say, oh my God, you know, this term is highly non-renormalizable, right? In all your quantum field theory textbooks, they told you to not look at non-renormalizable theories, and here I am, here we are. So let's just embrace this thing and see what happens, okay? So we're going to calculate a loop in the effective field theory. Okay, this is in the EFT, and these vertices are coming from this thing here. They're not some nice phi-4 interaction like you studied in your class. They are this beast. So the details are not important, but the dimensional analysis definitely is. What does this term look like? Well, I have this coefficient, phi squared d phi squared all squared, because I have two of these things. I have, oh, what do I have here? Oh, okay. I have an m to the 8th, okay? And then I have a single loop integral. Okay, I don't care about any factors, numerical factors. And then I have what? I have two propagators inside, so I'm just counting powers of k, but each one of these things here has 4, count them, 4 derivatives. So there's a k to the 4th squared, okay? So this is insanely UV divergent. And so what do I get? I get, so first of all, let's say the whole thing here is of order g to the 4th over m to the whatever 10th, okay? That's what this thing is of order, okay? And then I have lambda to the what? I have 8 powers, 12, oh, sorry, I have 2 powers here, right? So I have 8 minus 4, okay, these cancel, so I have 8 powers, okay. This is not working. Okay, I did something wrong here. Let's see. Okay, this is correct. Oh, I think this is 12, yeah, okay, right? Because these are each 1. And so then this should be, yeah, it makes sense. Okay, 8, yeah, that's correct, okay? And then I didn't show them here, but of course there are all these external momenta are also flowing through this diagram, okay? But if I'm looking at the UV divergent part, I can just expand in powers of that. So I'm going to get something like this. What am I doing? I'm going the wrong way. I'm going 6 lambda squared, okay? It's e to the 8th log lambda, and then finally, I get something finite. Okay, this is like log lambda over e. G has dimensions of mass. Because this thing is of order g squared over m squared. Okay, I'm sorry, I'm using a dimensionful coupling because it makes certain other things easier, but it makes the...
Sometimes it's confusing your sub-indices. I get confused some of your
Oh, okay. Yeah, these are just supposed to label the operator. I thought I was making things clearer. Instead of calling this C5, and you have to remember which is operator 5, this is just saying it's the coefficient. Oh, no, because I have the wrong one, because this should be, thank you. This is this operator, right? Yeah, I'm sorry. This is the correct operator, yeah? Okay? Why? This has mass dimension 8, so if I'm writing it in terms of this, do you object to this? Then if I square it, I get this squared over m to the 8th. I think it's correct now. I actually think it's correct after a bit of okay? Okay, but look, this is a qualitative discussion, okay? I mean, so yes.
Why can't it be just regular 5-4 interaction?
Oh, it can. Okay, I'm looking at the most troublesome, worrisome. This is why this unnamed Nobel Prize winner said that EFT was crap. I'm explaining that. Okay? And not just him. I don't think I'm giving away very much by revealing the sex, the gender. Okay, all right, so we have these horrible things, okay? And so just to emphasize, this is some sort of cutoff that we're using inside the EFT, okay? Which, I don't know, use your favorite cutoff, poly-VRs, whatever you like. It's not supposed to matter, right? So what do we do with these things, okay? So what do we do with things that have, 6 derivatives and are quadratically divergent? Well, the answer is you're just supposed to put in a counter term for every one of these things, okay? So all of these things right here, they are local in the sense that they are powers, they are integer powers of E. I can just make this a log of E over m, lambda over little m. So these are all local, and so they can be absorbed in counter terms, okay? So there's no problem, okay, except that there's an infinite proliferation of counter terms. Because if I take this thing, this is some super high dimension operator, I put it back into loops, I generate even more counter terms, and I have infinitely many counter terms. Okay, so this can be absorbed into counter terms, but there are infinitely many. That's the catch. Okay? And so the old guard would tell you, this theory is not predictive. This theory is not predictive. Okay? But remember, how are we getting this theory? Remember top down? This is our actual theory, right? This theory that we're writing here is tasked with reproducing this theory, okay? So all of these counter terms, they're not arbitrary. They're completely fixed by matching onto this theory, right? There's no arbitrariness here other than what I have in the fundamental theory, okay? All right? So what I claim is that of course, if I don't know the fundamental theory, maybe I don't know, but if I'm matching to the fundamental theory, guess what I get after I fix all of these counter terms? I just reproduce an expansion in powers of E over m. Basta, right? Okay? All right. But even this example was a little bit simple. Okay, so let's do a more challenging example. Okay, because, see, in this case right here, let me talk a little bit about how this matching, let me say a little more about how this matching works, okay, because I really want to try to convince you that this is not, do you have a question? Yeah.
No, but you mentioned you'll have infinite counter terms, so how do you match infinite counter terms?
It's like doing this Taylor expansion to infinite order. I don't need the infinite counter terms. Remember, I'm at low energies, so you tell me how much accuracy you want, and then for that accuracy I need, no, it's a great question, I need a finite number of terms, okay? So it's exactly, remember the two regimes in the multipole expansion. We're in the regime where we're far away. We're happy with the multipole expansion, okay? Okay, so actually, yeah, I think I'm going to do this. Okay, I'm not going to skip anything. I don't know how I'm doing with time. I haven't given these lectures before. Okay, so let's just see how it goes. Okay, is there a way that this is a question for the organizers? Is there a way to collect anonymous feedback from the target audience here? Because if there were, I would want to know. I'd like some feedback about whether I'm going too fast, too slow, where I am in that, okay? And I want you to be honest. I'm not going to ask you to raise your hands because I've never found that to be useful, okay? But I think maybe that would be useful because I'm not sure, okay? But I'm just going to for now, I'm just going to keep going according to my plan, okay? So let's imagine that we're doing this matching to higher order. I want to substantiate this claim that if we do the matching, everything will just be like, we'll just reproduce an expansion in powers of E over M, and that's it. So I'm not going to draw all the cross diagram, but this is essentially up to crossing. This is the only diagram at order G squared. Now, if I just keep doing higher orders in perturbation theory, what kinds of diagrams do I see? I would see diagrams that look, for example, like this. I would see vertex corrections, okay? Then I would also see diagrams that look like this, okay? And then I would see diagrams that look like box diagrams, okay? And there are even more, okay? I can draw diagrams like this, okay? There are also external leg corrections. There are other things I can write. So there's a whole bunch of diagrams that come in at order G to the fourth in the fundamental theory. And now, these diagrams are themselves UV divergent, right? They're themselves UV divergent. This theory has UV divergences. So for example, for this diagram here, I would have to include a counter term in the fundamental theory that looks like this, right? And for this diagram here, I would have to include a counter term in the effective theory that looks like this. Okay, and for this one here, I have to include sort of this kind of counter term. Okay? Now, how do we choose the counter terms in the fundamental theory? Well, if this is the most fundamental description of physics that I have, I'm just going to determine them by matching to experiment. Okay? So let's just assume that's the case. So these are just experimental numbers. Some of them I'm going to have to introduce some of the couplings that I left off over here, okay? I don't want to try to give a complete story. I want to try to give an understandable story. So I'm just going to focus on this thing right here, okay? So the reason I'm focusing on this is because notice that these are loops of light particles here, right? These are loops of the light particles. Those are a little bit more subtle to understand. So I want to explain how is it possible if I expand this in powers of E over M, it's not so obvious that I can expand this in powers of E over M, right? Does everybody see why? Because this guy has mass little m, these propagators have mass big M, but the loop here has mass little m. Okay, so in fact, what does this loop look like? Okay, if I actually just calculate this diagram, okay, so now I'm going to add to it the counter term diagram. Sorry, this would be a dashed line here. Okay, so I'm going to add the counter term diagram. And so remember, what does the counter term do? It makes things independent of the cutoff, right? So I'm not going to skip all the steps. I'm going to assume I've done that. So I have G to the fourth. I have a loop factor, 1 over 16 pi squared. I have an M to the fourth, okay? And then this is all at the squiggly level. I have some local piece, which is independent of energy, okay? But then I have a non-analytic piece, which is a function of E over little m. For example, if the energy flowing through here is bigger than twice little m, there's going to be a threshold, right? A non-analytic feature. So this function f of E over little m is a complicated, not that complicated, but it's a non-analytic function, okay? And then at higher orders, I start getting powers of e squared over m squared. Okay? So this doesn't look like an expansion in e over capital M, right? Okay? But then, remember, this is calculated in the fundamental theory, okay? When I match to the effective theory, I also have to include all the diagrams at the same order in the fundamental theory. So in other words, what matching really says is it says if I compute some amplitude in the fundamental theory, I am requiring it to be equal to the same amplitude computed in the EFT. Okay? So this exclamation point means this is a definition or something I'm requiring. And the claim is that all of these coefficients, well, now I erased it. It was here. All the coefficients that I could possibly write in the EFT are all uniquely fixed by making this requirement. And what I mean by equality here is I'm doing perturbation theory, so I compute both sides to the same order in whatever perturbative expansion I'm doing. So what that means is that this term right here has not just the tree-level counter term. So at tree level, this counter term was fixed by matching onto this. That gave me that infinite Taylor series that I wrote before. But now I'm working at one higher loop, so this thing has a contribution that looks like this. Okay? And what does this look like? It looks like g to the fourth over 16 pi squared m squared. It again has a constant term, and it has a non-analytic term, right? Because I have a two-particle threshold here, for example. And guess what? It's exactly the same function, f e over m, that I had over there. And it has exactly the same coefficient. So this and this cancel in this matching. Okay? That is not a coincidence. Because why? Because remember, at order g squared, I already matched here. And that means that the sort of low energy part of this diagram is indistinguishable from the low energy part of this diagram, right? If you basically, the lowest order matching was shrinking this heavy propagator to 0 and replacing it by an infinite number of terms. Now I shrink these two guys to 0, replace it by an infinite number of terms. Guess what diagram I get? This one. And if the coefficients are precisely made so that the IR part cancels. So you can start to see how this works, okay? And it really does work. So the non-analytic, the answer is that in the fundamental theory, there definitely are diagrams that have non-analytic structure at the low mass scale, but they're precisely reproduced automatically in the EFT such that okay, I erased it, but such that these coefficients are all just determined by this matching, okay? So that's the finish of my derivation or my explanation of how EFT works from the top down. So any questions on this? Yeah. So the coefficients, the statement is that the coefficients, so I have some CO, okay, all right, and this CO is just some well-defined number, okay, and when I choose my COs in my effective field theory that I wish I hadn't erased right here, then that reproduces at each loop order, if I've matched to that loop order, it matches the expansion in E over capital M of the fundamental theory. Was that clear enough?
I mean, when we wrote that diagram, we just had e to the 8 lambda to the 8 just some linear terms adding up. So I didn't quite see it clearly when you're getting this.
So let me try to say it another way, because I think this is an important point. So I'm going to try one more time, and then maybe we can discuss it later if it just doesn't work. But this is only part of it, but this is, the truth in the fundamental theory. And so my EFT has to reproduce this term. It does that automatically, is the claim. And the pieces that are not automatic in the matching are of this polynomial type. Okay, that's the claim. Okay? Thanks for the question. Other questions? Yeah.
Yeah. So this first effective diagram, like the square one below the EFT, you drew?
This one,
No, the left one,
left.
below.
Oh, yeah, this is meant to be a counter term in the EFT.
It's the counter term summing all the counter terms.
Yes, it's going to have a very complicated Feynman rule. If I'm working at high orders, this would be a sum of many terms, if you like, right? But I'm just summarizing it. They all look like this.
So at the higher orders, there will be even more loops of order m, and then you will consider even more loops from the effective
Yeah, as long as the claim is that this keeps working, as long as you just keep doing the same expansion on both sides, okay, it keeps working.
Okay.
That's the claim. Okay,
Thank you.
and these are, these are proven statements. They're just at the same level as the proofs of renormalizability in perturbation theory. Yes.
Sorry, can you please again? Why is the Nobel Prize wrong? I mean, I didn't get it.
It's just that maybe it's just a philosophical question, okay? But the people, even if you read, this is not the person I'm talking about, but if you read Steve Weinberg's Nobel lectures, he will tell you that one of the key clues to coming up with the theory of the weak interactions was that it had to be renormalizable, okay? And that was an important clue in discovering the theory of the weak interactions, okay? Now, Weinberg himself later became one of the strongest advocates of this EFT, so he is not the Nobel Prize, the unnamed Nobel Prize winner I'm talking about, okay? But the people who would object to these theories, they would just say it doesn't have any predictive power because it has an infinite number of terms that you're not fixing. And so precisely to address that, that's why I started with this top-down picture, because I said that, look, this is not just some game that we play. We have in mind that there's some fundamental theory that's involved, and then I'm showing you that given this fundamental theory, we really do have an expansion in powers of E over the heavy scale. Okay? That's the idea.
Great, thank you.
Okay? All right. Okay, so that's the bottom line, okay? And so what we see in this example, again in my language of the multipole expansion, I've told you exactly what the charge distribution is, exactly, here's the fundamental theory, and we've just used it to show that the long distance description can be written as an EFT, okay, with a large number of terms. But now, in practice, we're usually not in that situation, okay? If we knew the fundamental theory, why don't we just calculate using the fundamental theory? Well, it turns out that EFT is a useful tool, even if you know the fundamental theory, okay, sometimes, because it allows you to make things systematic and separate scales and so on. But that's not the subject of this talk, okay? I'm looking at, I really want to take this seriously, right? What if we don't know the fundamental theory? Okay, so now let's take the bottom-up perspective, okay? So the bottom-up perspective is we don't know the fundamental theory, but we sort of are aware of this paradigm. So we want to see, can we interpret this effective field theory? Okay, so now I'm going to write it. Can we interpret some Lagrangian with an infinite number of terms like this as an EFT? Okay, so now I'm giving a little more meaning. So I'm going to simplify things a little bit, I'm going to impose a phi goes to minus phi symmetry, which I actually had in my fundamental theory, even though I didn't say it. Okay, and so I have a little bit fewer terms. Okay, so here's my, once again, here's my dimension 2 term. Here are my dimension 4 terms. Okay, and then the next term I can write, since I have only even powers, I'll have something like c phi to the 6 over m squared phi to the 6th. Okay? Oh, what am I writing here? I love it when I'm able to, the trifecta is when you say one thing, write another thing, and mean a third thing. That's what I think of as the trifecta of teaching. So I have accomplished that here, okay? Thank you. Okay, and then I have dimension 6, and I can keep going, okay? And now, now what I want to ask is, and so m right here, I'm always going to be having in mind eventually that m is going to be the scale where things break down, Okay, but for right now, let me just ask a very simple question about a Lagrangian like this, is that when is a coefficient like CO, when is it perturbative? Okay. Okay, so in other words, these COs, okay, are just some numbers, okay? I've just factored out the scale m. So far, m doesn't have any real meaning yet, okay? But when is CO perturbative for any of these operators here? If I just try to, so how do I check that? Well, I compute some amplitude, okay? And I first compute it with this operator CO set to 0. Okay, so I wouldn't do that for the kinetic term. That wouldn't really make a lot of sense, but we're not worried about the kinetic term, right? We're worried about all these other things. So all these other operators, it makes sense to set them to 0. And then I compute whatever my amplitude is, but then I'm going to start getting corrections that are powers of CO. So in other words, I'm just trying perturbation theory and just asking when does it work. So what is the first thing I'm going to get? The linear power in CO is going to come with a power of m given by the dimension of O minus 4, right? Okay, right, because that's how I've defined the COs, okay? But I've factored out the leading contribution. Yeah, question? So for example, if O is phi to the 4th, this is CO. So I'm sorry, O is just any of the operators that I'm putting into my Lagrangian, okay, except for the kinetic term, okay? Okay, so you see that each power of CO comes with, because the powers of m are just determined by the dimension of O in this way, right? And then by dimensional analysis, this is supposed to be dimensionless since I factored out the leading contribution, so it can only be some power of E to the same power. And E could be, you know, a Mandelstam variable, it could be the light mass, it could be any of those energy scales, okay? And then I would, of course, get terms even higher order in CO, okay? It doesn't matter. I'll do a 3-to-3 example in just a second. This is a pretty abstract discussion, so I'm going to do an example in a second, okay? But so this is the idea, is that it always looks like this, okay? And so the claim is that this is perturbative depending on whether this power is whether this quantity is bigger or smaller than 1. So remember, I'm fixing CO and asking under what circumstances can I treat this as a perturbation, okay? So if the dimension of the operator is less than 4, okay, then this power of E is negative, right? So the expansion is in powers of m over E to some positive power. You agree? Okay? And so what that means is that for any fixed value of C, then this expansion gets better and better the higher energy I go. It gets worse and worse the lower energy I go, okay? And so this is called a relevant operator, okay? The relevant comes from looking at the low energy side of the question, right? At low energies, this term gets more and more important, okay? This expansion gets worse and worse. What if O is, and notice that for O less than 4, how many operators do we have that are O less than 4? 1, right? We just have one operator that is relevant, okay? Now we look, if O is greater than 4, then it's E over m to some positive power, okay? And that means as we go to lower and lower energies, it becomes less and less important. This is called an irrelevant operator. Okay, and then finally, the case of equality, we have E to the 0, it's independent of energy, okay, and this is called marginal. Okay? Okay. And so what we see is that that just from dimensional analysis, okay, so now I'm finally starting to you're starting to see why this dimensional analysis is a good thing, I think, okay? Because just from this dimensional analysis, I can see that if I go to sufficiently low energies, the only operators that I would need to keep are the marginal and the relevant operators, right? Because if I go to lower and lower energies, these become less and less important, okay? So this incredibly simple observation completely revolutionized particle physics in the late 70s and early 80s. It's largely due to the insights of Ken Wilson, who taught us to think like this. Okay, and notice that, so the punchline is that low energies, we only need the relevant and the marginal interactions. Okay? But those used to have a different names. What do they used to call this? Renormalizable. So, in this understanding, it is not, as was once thought, that renormalizability is some grand principle that we have to impose on our theories to have them make sense. It's actually a much more simple and humble thing. It just says that all the non-renormalizable terms, now re-Christianed as irrelevant, are in fact more and more irrelevant at low energies. So the fact that the theory of the weak interactions is renormalizable is not some consistency condition, it's just the condition that it's a low energy approximation. That's the idea. Okay? Okay? Now, I'm still not done with this, okay? All right? So, so I want to put even more, so this is, as you can start to see, this is the situation that we actually are facing with the standard model of particle physics, right? So we really want to understand this, okay? Phenomenology is not like string theory where they can choose different problems every year. We are stuck with the same conceptual problems we've had for a long time. So we really need to dig deep here, okay? So I want to say this was very rough because you can say, wait a minute, what's the scale M? What are these coefficients, C? Okay, what's really going on here? Can I make this more quantitative, right? Like how irrelevant are these irrelevant operators? Questions like that. So I want to start addressing that. And this usually goes under the name of power counting, okay? So power counting means how do I tell at the squiggly level how important these various terms are, right? You should never write a paper without knowing the answer ahead of time, at least at the squiggly level. So the very simplest kind, let me just start with a very simple ansatz. Okay, to get started, I have to start somewhere. So I'm going to just make an ansatz that all of these coefficients CO are order 1. Okay, how about that? Okay, putting a question mark there because I'm saying, why not? That would be the simplest thing. Okay? And then what happens then is that immediately I see a problem. What's the problem? Do you see what the problem is? Here's this, I guess I erased the more general Lagrange. No, this is it. So what's wrong if all the COs are order 1? What's the problem? Well, look at the mass. There's the problem, right? Because if all the COs are order 1, the mass is of order capital M, and all of these terms are getting equally important at energies of order capital M. So I don't have a hierarchy, okay? So if I assume this, then what I find is that the mass of this thing is of order m squared. I have no hierarchy, okay? And remember, hierarchies are not just this thing that gives full employment to particle physicists. I tried to convince you at the beginning, and I hope I succeeded, that we simply can't do physics without hierarchies, okay? I don't know of any theory where we can calculate anything where we don't have, at least at the starting point, have some kind of hierarchy, okay? All right, so this doesn't work, okay? This fails. And this is, in fact, the first time we meet this problem, which is going to become a really serious problem. Right now, it's just a problem with some simple ansatz. So to go a little bit further, I'm not going to do this. I'm going to say that CO is of order 1, except for C phi squared, which is much smaller than 1. Okay? This is not beautiful, okay, but I'm just going to do it. Okay? Okay, since that's required by this is required if I want to have predictivity, right? If I want to have a predictive theory, okay, so I'm kind of forced to do this. And then the next thing is the simplest assumption I could possibly do, okay? So now, at the tree level, now I'm fine at the tree level because all of these terms now, if m is now a very large scale compared to the mass of my particle, this theory starts breaking down at energies of order m. Everything is fine at tree level. Yes? Are we good? Okay? But once again, I want to worry about the loops. Okay? From the bottom-up perspective this time. Okay? So let's just look at now we're just in the bottom-up perspective, so I'm just looking again at my 2-to-2 scattering.
Hey, Professor.
Yes, sorry.
Are you going to expand on why we need hierarchy to predict, to be able to predict stuff?
Okay, so I gave several examples. So let's take fluid dynamics, for example, right? It requires you to be looking in a regime which is where you're looking at long distances compared to the fundamental scale, okay? And every single theory of, any predictive theory of condensed matter works the same way. Every theory I know in physics works this way.
Okay.
Okay? So I really, this is what I mean by saying I want to bring the standard model back to Earth, okay? I claim this is not some weird, hierarchy is not some weird thing that, Ken Wilson, Lenny Susskind, and other people explain to us. It's really baked into the way we do physics normally, right? We can talk about the universe because we're not trying to describe every detail, et cetera, et cetera, et cetera. Okay? All right? And in this case here, it breaks down in a very concrete way. If the mass is of order m, then as soon as we're able to make these phi particles that have any sort of relativistic interaction, all of these infinitely many terms would be the same size if all the c's were the same, were order 1. Okay? So clearly, that's not an acceptable situation. So this is just the simplest ansatz I can make where I still have a predictive theory. Okay? It's just a provisional thing I'm doing to make some points. Okay? So now let's look at this EFT. Let's look at loops from the bottom up. Okay, I have some tree-level interactions. I have some one-loop interactions. Okay? Okay, and now, okay, again, I'm going to have some I'm going to have some I'm going to have some kind of higher dimension operators. And so let's see. So I'm feeling I'm going to feel like I'm going to get all the dimensional analysis wrong. But okay, let me just do this. Okay, I think this is right. Yes, I have it wrong in my notes, so I'm correcting it on the fly. Okay, so that's why. Okay, so this is good enough, okay? I can look at things that are even more UV divergent, but that's fine, okay? So now, okay, now our unnamed Nobel Prize winner really gets going, okay? Because they say, look, now you don't know the fundamental theory, okay? And now this thing right here, this scale is what? I don't know, going to infinity or as high as you want, okay? So you have no control over these terms. You can't tell me that they're small, okay? So I'm inserting this operator, phi squared d phi squared. You're telling me I have to square it? Okay, I'm going to put in c phi to the 4th. I'm going to do a mixed term. But you're right. This term right here, I'm putting in phi squared. It doesn't matter, but let me get it right, okay, anyway, okay, all right, to make everybody happy. So this is just one of an infinite number of examples, so I'm doing a phi squared d phi squared here and a phi to the 4th here. So I should have 2 couplings and then 1 over m squared, just so I don't have to erase. Yeah? Yeah. Shut up. Okay? I could come up with another. This is all dimensional analysis. You're right. Okay, you're right. But this is dimensional analysis, so, okay? This is a wise guy. I don't know. Okay? Yeah, he's right because there are these field redefinitions, blah, blah, blah. Okay? And so I am, if I made this d phi to the fourth, then you couldn't get rid of it. There's no way to get rid of it, and then I just have to erase and write something with even more divergences, okay? But my point would remain the same, okay? But yes, thank you for that. If I ever write this up, I'll try to make sure that that's correct. Okay, so what do we say to our unnamed interlocutor? So the thing is that at this point, okay, we have to appeal to the top-down picture, okay? I don't know what the fundamental theory is, but I believe there is a fundamental theory, okay? I am a realist. I don't believe this is some stupid game, okay? I believe that if this is an approximation, it's an approximation to something, okay? All right? And so if this thing was an approximation to a theory of any kind that breaks down at the high scale, okay, then that matching will tell me what the EFT counterterm is, okay? And what will it tell me to put in? It will tell me to put in my coefficients, okay? And it's going to tell me to put in, for this thing, to put in something like m squared minus lambda EFT squared, okay? And for this one, it's going to ask me to put in some e squared times log lambda EFT over m, okay? Such that this exactly cancels that, and I'm left with an expansion in powers of e over capital M, okay? So I do have to appeal to some sort of top-down picture, but I don't have to tell you, the claim is I don't have to tell you, crucially, I don't have to tell you what exactly is the fundamental theory, just that it's some fundamental theory that exists and it has a scale of new physics m, so it does in fact have this kind of an expansion, which is what I showed before from the top-down picture. Okay, does that make sense? Okay. But notice what just happened here. What just happened here? This theory, we renormalized it. We got rid of this lambda EFT by matching onto some more fundamental description. Why did this disappear in the matching? Why does lambda EFT dependence disappear in the matching? Because the fundamental theory doesn't know about lambda EFT. Lambda EFT could be dim reg, it could be Pauli-Viars, it's whatever we as a theorist are using to calculate. It's a matter of convenience. There is no way the fundamental theory knows about lambda EFT. That's why the lambda EFT dependence goes away. In other words, renormalization is exactly EFT. And I mean it 150%, okay? All right? So notice what this does in the context of EFT. It is effectively replacing the EFT cutoff with the scale m. But I'm not saying that lambda EFT is a number of order m. I'm not saying that. I'm saying that matching to a theory, that a realistic theory that has new physics at the scale m, gets rid of the EFT, lambda EFT dependence and replaces it with m dependence. That's what renormalization is. Okay? We don't know what the scale m is, but this is what's happening. Okay? So any questions on this? Sure. It's Martinius Veltman. Okay, if you buy me a beer, I'll tell you a story about him and me. Anyway, you have to buy me a beer. Yes?
Markus, I have a question there because when you are computing this matching normally, your Wilson coefficients, they have a dependence on the scale. But you're saying that they get canceled. I don't see how this happens.
Okay, so sorry. So let's be clear what I said and didn't say. So I probably, maybe I said something confusing. So what I was trying to say is that what gets exactly canceled is the dependence on this lambda EFT. Okay, that is what is exactly canceled. But absolutely, the leftover coefficients have dependence on the scale m, which is a realistic thing. M is actually the scale where something new is happening, some new physics is coming in. Okay, just like in the fluid, right, there's a scale where it really breaks down and you need some new description. It's exactly the same thing.
Then at the end of the story, this M is which is taking control of this scale dependence always.
Yes. So, of course, it could be more complicated. Here, I've assumed that there's a single scale, capital M, that controls everything. That's obviously not necessarily the case. And in fact, we will see there's evidence for multiple scales of new physics in the standard model. But yes, that you have it, that's the paradigm.
Okay, thank you.
Yeah. Okay. Okay, so I think that's, I think I just, I mean, I could start another topic, but I think it may be better just to, if there are no questions, I'm going to start another topic, okay? Because you guys have interrupted me a lot. So this is, anybody want to ask any questions? Is that okay with the organizers? If nobody's asking questions, should I just keep going?
Yeah, I suppose.
Yeah?
You have
Okay.
15 minutes.
Yeah, I have 15 minutes. I know I'm not over time. Okay, so now I'd like to refine this a little bit more. Okay, so in a little more quantitative way. Okay, so this simple thing that I talked about, where we took all the C's to be order 1 with this major footnote, except for one of them, the one and only relevant operator in the theory, if you notice. We'll come back to that. What I really want to get to next is I want to emphasize that this EFT ideology really does work, okay, in cases that we know. Because so far, this looks a bit dodgy, right? I've made this major caveat here, okay? So the next part of what I'm going to do is to try to show you cases that we know, that we understand, where this ideology works very well, okay? And the spoiler alert, it's everything in the standard model works like this. Within the standard model, we have tons of hierarchies. We understand the EFTs in exactly this language. It works beautifully, just like it does in every other area of physics. So this is the first, now I'm taking the first step in this. I want to talk about a more refined power counting. Okay? So before I just said, well, maybe all these C's are order 1. Okay? So now I'm going to, suppose I have a single scalar. The generalization to more complicated cases will be obvious. So it's going to contain an infinite number of terms, okay? And there's going to be, each term is going to have, let's say, L derivatives and phi, and N phi fields. So it's, again, a single scalar, okay? And then I have some coefficient. Of course, really, there are generally more than one of these terms, but you get the idea. And then, again, I have the scale m, n plus L minus 4, okay? So that's just put in so that these C's are dimensionless, okay? So now my more refined ansatz, okay, is going to be that CNL is going to be of order G star to the n minus 2, okay? So you can't read that, n minus 2, okay? Okay, and so where is this coming from? Let me try to explain a bit where this is coming from, okay? So the claim is going to be, okay, that when I do this, I can think of G star as being a dimensionless coupling strength, okay? All right, so let me explain that, okay? So first of all, notice that if I adopt this ansatz, then I can write my EFT in the following way: m to the 4th over G star squared times some function of d over m and G star phi over m, okay? Right, so I've just, by adopting this scaling, I can write the theory in this way, okay? And so what I'm really supposed to be doing is, of course, this is not something like a hypergeometric function or anything. I'm imagining this is some Taylor series that I'm taking out to as far as I like to get the accuracy that I want, right? That's what I'm doing here. And so I should just think of this as an expansion in powers of these things, okay? And so what you see here is that every time you add a scalar to some operator, right, you get an additional factor of g squared over m, right? That's what this is saying. If I expand this out, I'm expanding in powers of phi g star over m if I'm expanding in this, right? So each scalar costs another g star over m. So that sort of tells you why g star is a coupling constant. It's the cost, the suppression factor associated with emitting another scalar, okay? Also, if you remember that in perturbation theory, if you write the action as S over H bar, so temporarily restoring the factors of H bar, then H bar acts as a loop counting parameter, right? Okay? And so this actually tells me that the loops, if I look at this prefactor, the loops are suppressed by G star squared over 16 pi squared, okay? And that's, again, what I would expect from a dimensionless coupling strength, okay? So, again, to put a little more flesh on this, let's look at just do some examples, okay? So if I just have a standard cubic coupling, that's of order G star times M, okay? On the other hand, a quartic coupling would be of order G star squared. A coupling of 5 guys, if such a thing existed, would be G star cubed over M, and so on. Okay? So you can see that if G star is large, this is becoming a more strongly coupled theory. If I look at loops, for example, a loop like this, okay, then this is of order G star cubed. By dimensional analysis, there's an M, and there's a 16 pi squared, right? If I just honestly do this diagram, that's what I get. 3 powers of G, 1 power of M by dimensional analysis, loop factor, and guess what? That's what I said was a loop factor down from that, okay? And you can keep going like this, and you can convince yourself that, that this is true, that I said. Loops are suppressed by powers of G squared over 16 pi squared, and, okay? Now, this is just some ansatz. I just pulled it out of the air, so to speak, okay? And, notice that from this, I would expect that perturbation theory breaks down, so when G squared becomes of order 4 pi, or even larger, right, then perturbation theory is invalid, right? Perturbation theory breaks down, okay? And so this suggests, because remember, this is supposed to be an EFT. It's supposed to mean something, okay? It's supposed to be predictive. This suggests, okay, this means suggests that, in fact, G star is less than of order 4 pi, okay? Now, do you believe this? You shouldn't. You shouldn't believe it based on what I've just said. This is just some ansatz. But this very simple ansatz turns out that it works in an amazing number of cases. Okay? So this, just empirically, this works in many cases of interest. Okay? I don't want to say all, but I can't think of any case where it fails. So for example, this is the last thing I'm going to say, I'm aware of the time. In Fermi theory, the low energy theory of beta decay, right? The scale where the theory breaks down is of order MW, and G star is of order G weak. So you can just draw lots of diagrams, and you can convince yourself that you actually do get this counting, okay, from just integrating out the W, or maybe the Z too, okay? Another very different case where this works is the pion EFT. So in other words, if you look below the scale lambda QCD, you have an effective theory of pions, maybe kaons and etas, and in that case, the scale where that theory breaks down is of order the rho mass, the first sort of heavy QCD resonance that you've left out, and G star is actually of order 4 pi over root the number of colors. So if the number of colors is 3, this is a number of order 1, but for large n, this reproduces all of the large n counting, Okay, so, and this substantiates the fact that at large n, the theory of mesons becomes weakly coupled. Okay, and another example that's a little bit near and dear to my heart is Seiberg-Witten theory. And the reason is because people generally who work on Seiberg-Witten theory are too good to talk to people like me and who care about things like factors of 4 pi. So a long time ago, Riccardo Rattazzi and I investigated. We can calculate a lot of things in Seiberg-Witten theory, including supersymmetry breaking things. And it turns out that this kind of scaling is perfect. And it's perfect with M being of order the super-Yang-Mills scale, where all the strong dynamics is supposed to happen in that theory, and G star is of order 4 pi, okay? And there are many other cases, okay? So this is where I'm going to stop, okay? Because the next topic is really, actually the next part, I'm going to start with this, so this is a very natural breaking point. I can't believe this happened. It's some kind of fine-tuning, okay? I'm actually at the end of my first topic, at the end of the first lecture. So we're going to continue with this next time. We're going to start talking about how symmetry plays into this whole story. Okay, thanks.
More questions, a couple of questions. We have a session later on today, but if you...
Yeah, I mean, kind of a silly question. Why is it called power counting? It's essentially because you're...
I didn't name it that. I think it's because, I don't know, power. I think the power just refers to like powers of the scale m, I think is really all it means. Yeah. But I don't know. I don't know why it's called that.
But it's just this process of expanding in the powers of the derivative. And
yeah, it's a rule. So the idea is, the basic idea in power counting is that you have a scale m where the theory breaks down, and what is the rough rule at the squiggly level for assigning the coefficients, okay? So the first rule I had was all the C's are order 1 except for one of them. They have a special rule for. Now I've talked about a more general rule, and I'm going to show you that within the standard model, this rule works perfectly. So I've already sort of foreshadowed this here, but that's the claim. So the claim is that I'm going to put more meat on these bones and say that this is, as far as we can tell, this is the way the world really works. Okay?
Okay, thank you.
This one... No, it's okay.
So how is this refined power counting modified exactly when you have more than one type of field?
So the place that adding more fields is perfectly okay. You know, if I had a fermion field, I would just have the same G star, a fermion field, and m to the 3/2, you know, G star gauge field over m or whatever. Okay, so adding more fields is no problem. You should question though, why is there just one scale m and one coupling strength? Okay, in the standard model, I have couplings that span many orders of magnitude. So this is a sort of a simplified description, okay, for sure. Okay, so for example, even in Fermi theory, you know that mixing effects are very suppressed. Okay, so they would not obey this power counting. And in the fundamental theory, we understand that because there are small numbers in the fundamental theory, namely the standard model. And so, you know, this is still an oversimplified thing, but it's incredibly useful in many cases. Okay, and the symmetry part is going to be precisely what do we do if there are small parameters in the theory, okay, like in the standard model. We have to augment this with some more information, okay, and that's going to turn out to be related to symmetries.
Thank you.
Can I say that the rule that you give is basically assuming that the UV is a local quantum field theory?
No, I think it's much more, it has a much stronger assumption than that. I mean, for example, why should the power counting of any operator be given in terms of two quantities, right? M over G star. I mean, what I'm saying is that, I think what I would say is that this is the power counting I would expect in a theory that has just one scale and then one sort of characteristic strength of the interactions, right? Like in the case of the pion effective theory, when we go to the scale where the theory breaks down, it's fully strongly interacting, right? And so for small n, the coupling is 4 pi. Whereas in Fermi theory, when we come to the scale where the theory breaks down, it's still weakly interacting. And as long as we can characterize it by a single scale and a single coupling strength, I would say this is what I would expect.
So, for example, if the UV is string theory and we have just one string coupling,
yeah, I would expect I would expect this to hold for string theory. I don't know anything about string theory, but if you could convince me that there really was one scale and sort of one coupling strength, then I would expect this to be correct. Okay, and like I said, it's really impressive for cyber-Gritton theory. We have all these plots, where people had calculated some of these things, and if you look at their diagrams, they have axes that have like 10 to the minus 6, scale on them or something. We factor out all these 4 pi's, and everything goes between like 0 and 3 or something. Okay, every coefficient in the effective theory is really of order 1. I mean, cyber-Gritton is basically string theory, no? I mean, anyway.
Questions? No more questions? Right, so then let's thank Markus again and go for a coffee break.
Thank you. Yes.
Come back in half an hour.